4.2. Hmm? 4.2 number 2. Hmm? Theo, you sure it's number 2? You got number 2.
Oh, I got it right. It's just I guessed on that one, and I somehow got it right.
I see. Okay. In this problem, Rolle's theorem determine whether it is possible for the function to have 2 or more real roots. Okay. If it's possible for fx equal to 0 to have 2 or more solution. So I would say for a problem like this, you just follow the lead by the question, right? Number 1, according to Rolle's theorem, this one is clearly continuous, right, and differentiable, right? Therefore, if you have 2 points, which means 2 roots, then f prime c equal to 0 for some c a b. Being said, if you have something like this, and this function touch this one at 2 points, then somewhere in between, your derivative is going to be 0. With that in mind, therefore, you check the derivative, and you find no matter which x you plug in, this is always positive or 0. Plus 7, this is definitely bigger or equal than 7. Cannot be 0. So like the example we showed in class, we prove by contradiction. If there are 2, this happen, but if this happen, there will be a contradiction. Therefore, this cannot happen. Okay, so contradicts 2, f prime c equal to 0. Therefore, fx cannot have more than 2. Let's say 2 or more solution. Because if it has, then there is a contradiction. Okay, so that's number 2. Now number 5. We have a function. Now we first verify that this one satisfies the hypothesis of the mean value theorem. Well, is this one continuous on 1 to 15? Is this one differentiable? The answer is yes. Therefore, by mean value theorem, there exists a x such that this one is fb minus fa divided by b minus a. That's where you have the average velocity equal to your exact velocity. Your job is try to find what is x. Okay, so f prime x equals fb minus fa divided by b minus a. You can simply just add this f15 minus f1 divided by 15 minus 1, which is ln 10. Then you just take the reciprocal since it's 1 over x. Use the property of log, you have 14 over ln 15. All right, that's number 2 and number 5. Other questions from homework? All right, let's continue. So 4.3, we finished how to draw the maximum, minimum, increasing, decreasing, inflection points, concave up, concave down, all the kind of things. But basically just putting the second derivative and the first derivative together, you can do it. Now we want to go into 4.4, which is called indeterminate value. And the L'Hopital's rule. All right. Now, let's talk about indeterminate form. What do you mean by indeterminate form? Well, when we do the limits, we know now that it's very easy for us to see 0 and infinity. But let's say if we take a limit of something, and then we find, well, it's 2 over 3, then it's determinant. The answer is just going to be 2 over 3. If you have 2 over infinity, that's not too bad. It's just going to be 0. If it has 1 over 0, we know it's roughly going to be like positive or negative infinity. So all those kind of things by common sense, we can know roughly what they are. Sounds good? There are something called indeterminate. That is, just by looking at the number when we plug in, we cannot easily tell what they are. For example, 0 over 0. What is it? Is it 1? Is it infinity? Is it 0? We have done this before, right? It really depends on how big is the top and how big is the bottom. It can be anything. Another indeterminate form is infinity over infinity. For example, limit x goes to infinity, x cubed plus x squared divided by x squared minus 1. What's infinity over infinity? It really depends on what kind of infinity you have on the top and the bottom and which one is bigger. That's when we go over the whole thing about leading terms. Still okay? So these are the harder ones. We call them indeterminate. For this case, we want to handle not only these two, but every single one of them. And we have 7 different cases. Everything else is actually determinate. It's not hard to do. So who are they? 0 over 0, infinity over infinity. 0 times infinity. Infinity minus infinity. 0 to the 0, 1 to the infinity, and finally infinity to the 0. Okay, I will give you some example. Talking about this. Okay, limit x goes to 0 plus x times ln x. What's the limit? Well, if you just look at this, the limit is 0. 0 times anything is 0. Okay. Meanwhile, if you look at ln x, okay, this is negative infinity when x goes to 0 plus. And the infinity times anything is going to be infinity. Make sense so far? That is why this is hard, because this one is technically not 0. It's a little bit positive. A little bit positive. Anything positive times infinity should be infinity. But meanwhile, anything close to 0 times anything is going to be 0. So that's why it is hard, indeterminate. Similar cases for something like this. For example, limit x goes to 0, x to the x. This is clearly a 0 to the 0 case. Okay. What should it be? Well, anything to the 0 should be 1. Make sense so far? Meanwhile, 0 to anything should be 0. So what about 0 to the 0? Hard to say. Indeterminate. Okay. Later we will see all of these will be indeterminate just by looking at examples. It's hard to tell. Similarly for this, anything to the infinity should be infinity. However, for example, 1.1 to the infinity. However, 1 to anything should go to 1. So which one should this one go to? Indeterminate. Infinity to the 0. Well, infinity to the point 0.00001 power should still be infinity. Meanwhile, anything to the 0 should be 1. This one's right in the middle. Okay. Sounds good? So that's the 7 things we want to handle. Now, how do we handle it? We do it by L'Hopital's rule. Okay. Let me write down what it means. If f, x, and gx are differentiable at x equals a, okay, then limit x goes to a, fx over gx equals limit x goes to a, f prime x over g prime x. I cannot say at x equal to a, I should be differentiable in the interval. Containing a. Okay. Then this will happen. That is called the L'Hopital's rule. Given that, we have 0 over 0 or infinity over infinity case. All right, let's talk about what it means. Number 1, this is pronounced L'Hopital, not L'Hospital. Okay, so whatever you have with this one, do not pronounce it in the wrong way. Do you guys know the story how L'Hopital's rule is discovered? Do you know who discovered L'Hopital's rule? His name is Rohan Bernoulli.
Why would he discover something and then not name it after himself?
What do you think?
I don't know.
He was actually tutoring L'Hopital. L'Hopital was super rich. Okay, L'Hopital just say, "Hey, Johan, let's just do some math together. You tutor me, I pay you a handful of reward. But anything we discovered during the tutoring, I will name them. They will be named after me." Okay, so basically that's what happened. Johann Bernoulli actually discovered L'Hopital's rule, but L'Hopital took it because he's paying. Okay, so this kind of story actually happens a lot in the history. You can go back. Anything that's named after a company, usually it's actually discovered by some individual, but they are not allowed to actually put their name in front of it. This guy is very interesting. He has a brother, older brother, Jacob Bernoulli. He has a son whose name was, I think, Daniel Bernoulli. So all his life, he lives in the shadow of his brother because his brother is a mathematician. His brother was actually a really good mathematician. So he just said, okay, we came from a rich family. He's supposed to be a businessman, but then he became a mathematician. Then their family just say, hey, Johann, you are the second son. You want to be a businessman to inherit all our family wealth. But he said, no, I want to be a mathematician because I want to compete with my brother. He became good, and he went to the same university asking for a job, but they just rejected him because they said, we only need one Bernoulli in our university, and that is your big brother. Okay? And his brother is so talented, so he just said, I want to develop something else. I want to be a really good athlete. So he runs really, really good. And a lot of people just say, look at him and just say, wow, look, Professor Bernoulli can run. So they actually mistaken him to be Jacob Bernoulli. So whatever he does, people just give the credit to his brother. Okay, so he lives in the shadow for all his life until his brother died at the age of 55. So finally, he became the only Bernoulli who is good with mathematics. But then his son became a famous mathematician. Okay, and his son actually won a really big mathematics prize the same year he wins it. So basically, they were trying to actually do something nice, right? You see, like a father and son win the same prize at the same time. Isn't that great? But he was super jealous of his son and just say, okay, you cannot go into my house today because you win the same awards as me. Okay, so go and find your own place. He was super pissed. And then Daniel Bernoulli was a really interesting guy. He developed the whole thing about fluid dynamics, which is a big deal. It is such a big deal, such that Johann Bernoulli, his father, actually tried to steal his work. He actually tried to collect everything his son talked with him and write them into a book and published it before his son published it. So he will be the founding father of fluid dynamics. But then because Daniel Bernoulli has so many friends and they say, well, Daniel has been communicating these ideas with us 2 years ago. You know, your thing cannot be original. And every calculation you have there is actually by Daniel. So it ended up being a really big scandal. So Johann Bernoulli was really interesting. He developed some small discoveries, not so big, but he lives in the shadow, first under the shadow of his older brother, but then his own son. And he's really jealous of both of them. So, well, that's an interesting figure. He didn't even get the L'Hopital's rule, which is sad. By the way, Euler was Daniel Bernoulli's tutor. So all these guys are connected. Okay. Let's just put tutor for mathematics. All right. So we got the rule. What does it say? It basically says this. Number one, we had this one before. Okay. We go through all kinds of trouble by drawing the circles and everything. We discovered this is one. But now it says you don't have to worry about it anymore. Plug 0, what do you have? 0 of 0 case. Here. And it's differentiable. Therefore, you trigger the L'Hopital's rule. Which means whenever you try to find the limit of this, it's the same as finding the limit, going to the same point, the derivative of this, which is this. Derivative of sine, cosine, derivative of x, 1. Can you plug in 0? Well, that is going to be cosine 0 over 1, which is 1 over 1, which is 1. So forget about every geometry we did before. By L'Hopital's rule, we just have this answer. L'Hopital's rule happens here. When you write the limit to be the same as the limit of the top and the bottom both taking the derivative.
Would you not have to do like the division rule? Like you just do them separately?
Beautiful. This is the quotient rule.
Or yeah.
You use it when you are trying to find the derivative of this quotient. However, for L'Hopital, what you're really doing is you're trying to find the limit. So it's a big irony. The wrong quotient rule is actually the right way to do L'Hopital's limit. Can you see you're trying to calculate two different things?
Yeah, that makes sense.
Cool then. So don't mix them. It doesn't say that you can do quotient rule from now in this way. Okay, you have a limit in the front. If you have you have no limit sign, don't even go there. That's fantastic. Okay, let's think about it. Do you have something like this before? Okay. How do you do it? Well, you plug in. You have 1, 0 over 0. Then you'll say, well, conjugate if possible, right? We all go over all those kind of algebras, which is not reliable at all. Sounds good? But now you don't have to do it anymore. Number one, verify. Well, it's zero case. Therefore, I can use L'Hopital's rule. Then what I do is take the limit, take the derivative of each. Bottom is 1. The top is 1 over minus 0. What's the limit? Well, that's going to be 1 over 2 divided by 1, which is 1/2. No conjugate, no anything. Just take the derivatives. Of course, L'Hopital's rule happens here when you can take the derivative. Sounds good? Okay. Something we had before, example. Leading terms. What's the limit when x goes to infinity? X cubed plus 2x squared minus x divided by 3x cubed minus 2. Okay. Now by leading term, you know this is infinity over infinity, but we really ignore just this and that. We have 1/3. Sounds good? But now you don't have to memorize any of them. You just go there and apply L'Hopital's rule. Plug in. I do have infinity over infinity case. Well, then L'Hopital's rule works. Then derivative of the top. Derivative of the bottom. Good so far? Okay. Now, what's the limit? Plug in. Do you have infinity over infinity again? Yes, then L'Hopital's rule again. Okay. Plug in, what do you have? Infinity over infinity again. All right, then L'Hopital's rule again. What's the limit? 1/3. Does it make sense to everybody?
Okay.
Okay, so this is what L'Hopital's rule says. It can handle two cases, 0 over 0 or infinity over infinity. Once you have these two cases, just apply. And your hope is once you take the derivative, this one become easier than the previous one. Okay, so eventually if you keep doing this until one day, you will actually find the right answer because you can finally plug in. Okay, so far, we have verified this one works for everything we had before. Can this one also handle something that we could never handle before? The answer is definitely yes. Hold on, give me a second. Sine. X goes to 1. How do you handle this? Leading terms not working. Okay, basically everything before fail. Sounds good. But we have new tools. What's the limit of the top? Sine 0. That's 0. What's the limit on the bottom when x goes to 1? That's going to be 1 plus 1 minus 2. That's going to be 0. So we do have 0 over 0 case. Good so far? Once we have that, L'Hopital. After that, plug in 1 again. This is going to be 1/3. L'Hopital's rule. All right. This basically means you can forget about everything we learned before about taking limits. As long as you have 0 over 0 or infinity over infinity case. Conjugate, you won't need it anymore. Simplification, you don't need them anymore. Leading terms, you don't need them anymore. You just need L'Hopital's rule. So in the final exam, we will put all the finding limits together with derivatives and integrals later. By then, if you see a finding limit task, feel free to apply L'Hopital's rule. Okay, in exam 1, we cannot use it, but in final exam, when you go and find the limits, feel free to use L'Hopital's rule. Okay. Does everything make sense so far? Okay, so that's basically what L'Hopital's rule tells us. Of course, roughly we want to talk about why L'Hopital's rule is true. It looks pretty weird, even though it looks simple. Okay. Basically, you're just trying to say, hey, why limit x goes to a, fx over gx will equals limit x goes to a, f prime x over g prime x. Why are they the same? Of course, they are only the same when you have 0, 0 over 0 case or infinity over infinity. We won't give you the complete proof, but we can give you roughly the idea. This is a, okay. Let's say this is fx This is gx. And you have 0 over 0 case, so they both pass this point. Good so far? All right. Now what I'm going to do is I'm going to take this window, I'm going to make it look larger. Then we know if you take the window to be extremely small, these two things become almost straight as a line, which is their tangent line. Still okay? So even though they're not line, but roughly if you zoom in enough, the black one look like this, the red one look like this when you zoom in. Okay, now what are we talking about? You're talking about when you're very close to A, what is fx, which is this, divided by gx, which is this. Okay, now I'm telling you the ratio between them is the same as the ratio between the slope of these two lines. Okay, when x goes to A. Can you see it's true? Okay, the size of this divided by the size of this is the same as the slope of this black line divided by the slope of the red line. Of course it's the true because of the triangle. Okay, that's why L'Hopital's rule is true for 0 over 0 case. We cannot give you the proof for infinity over infinity, but roughly, I think you can trust it for now. All right. Is everything good so far? That's L'Hopital's rule. What does it do? Well, we have indeterminate form of limit. We have 7 of them. And L'Hopital's rule helps us to handle the first 2. Okay, we still have 5 left. Okay, that's what we will do next. Let's do them one by one. 0 times infinity. Let's go back to this example. Limit x goes to 0 plus x times ln x. Okay, plug in, you basically have 0 times negative infinity. Indeterminate. So how do you do this? You wish it's this or this, then I can use L'Hopital's rule, right? How do you change a multiplication to be a dividing? You take the reciprocal of one of them. Instead of times, you divide by the reciprocal. Does it make sense here? That will work. So let's do that trick. This one equals, well, just take one of them and make a reciprocal. Which one do we want to flip? Doesn't matter which one. Let's take the easier one. Still true, right? What's the top? The top is still negative infinity. What's the bottom? The bottom is 1 over 0 plus, which is infinity. Make sense so far? By flipping this one, you made it the infinity over infinity case. Therefore, you can use L'Hopital now. then what you have is derivative, which is zero. Sounds good? Okay, so let's summarize. What do you do with 0 times infinity case? Well, you have two choices. Flip one of them to make them dividing. You can either do this, 1 over 0 divided, infinity divided by 1 over 0, that's one case. Or keep the 0, do 1 over infinity. Flip one of them. Okay. For the first case, once you flip, it's not hard to see. You have the infinity minus infinity divided by infinity case. If you flip the bottom, you have 0 over 0 case. Does it matter which one? Not really, because they can all be handled with the L'Hopital's rule. Okay, so you have 2, 0 times infinity, you just flip one of them. Moreover, it doesn't matter which one you flip. Always doable.
I got a question.
Yep.
Would this still work if you had like 3 times like sine x, x, and ln x?
Hold on. 3 times what?
If you had like 3 terms, so like say you had like sine x, x, and ln x, would it be the same process?
Where is it? Example. Very good. So now what I want to say is this is 0 times infinity. Who is 0? This is 0. So when you have more than 3, you can always group 2 of them together. Make it just one term. So at least you can do this. And I'm pretty confident it's going to be 0 over infinity case. Okay, so you have to put these two together and do it. So 4, 5, 6, it's just a matter of complicated derivatives. So yeah, I shouldn't erase it. This is a good example. Just do this. And then use L'Hopital. Okay. So that's the first case. Second case and third case. Let's put all these cases together. Okay. Each one, I will give you an example. Or actually, let's just do the first example. Okay. This is 0 to the 0 case. Just as we said, this is indeterminate. Why? Let's take x to be very small. Okay. Like we said, anything to the 0 should be 1. Meanwhile, 0 to the anything should be 0. This one is right on the edge. It's not 0. It's a little bit bigger than 0. So you don't know which one to take. Okay. That's why it's indeterminate. Remember our goal. Our goal is to have something like this. So L'Hopital. Okay. What should we do?
Take the natural log.
Whenever you have a power, at least we should try this. Then lny, which is the limit, now our hope is this one is doable. Is this one doable? What is it? It's 0 times infinity. How to handle 0 times infinity? You flip one of them. This is the case we just did. Make sense so far? Okay, so just go ahead and try to do it. Infinity over infinity. Actually, it's exactly the same, so I will skip some steps. The answer is 0. Which is your L and Y. Now, what is Y? You just need to take in e to the 0 to have 1. Because technically, this is L and Y. Sounds good? Is this one always doable, or are we just lucky? Well, just take the general form. 0 to the 0, if you take ln, you got 0 times ln 0. What is ln 0? Negative infinity. So you actually always reduce to 0 times infinity case for this case. Okay. Wait a second. We have this. Indeterminate. Should we also take ln? Of course. What is ln1? 0.
0.
So we have infinity times 0. Again, 0 times infinity case we can handle. Finally, infinity to the 0. We have 0 times ln infinity. What is ln infinity? Infinity. Therefore, we have 0 times infinity. So actually, also, although we have 3 different cases, but once you take the log, they all reduce to the same thing. With the same thing, you just flip and use L'Hopital. We have 7 indeterminate forms. L'Hopital helps us to handle the first 2. For this one, you flip. You can use L'Hopital. For these 3, you just do ln. They all become the third case. We only have 1 more case left. Sounds good? Okay. The last case, there's no general way of doing it. So this, we just say it's hard. You need to be a little bit lucky so you can handle it. For the first 6, now we have a standard way. All right. Let's try one by yourself. What's the limit? Indeterminate. But as we said, take the log, try to finish. All right, that will be the complete work. Any questions? All right. You have been told this fact a long time ago when you do compound interest. That is, when n goes to infinity, 1 plus 1 over n to the n equals e. We never told you why. Finally, for now, you do have an answer. The limit is e, and you did it by L'Hopital's rule. Okay, from now on, anything like this, you will be able to do it by yourself. Do we need more examples? If yes, just click. We don't have time for now, but we can do it next time. Okay, so this is what I'm going to do. I'm going to open the homework today for 4.4. You try 1 or 2, okay? And if you get stuck, just bring them on Wednesday. Meanwhile, on Wednesday at the beginning, if nobody asks any question from the homework, I will then do this poll again. And if more than 3 people want more example, I can certainly give you more. Okay, let's shoot for that. All right, that's all for today.